The final identities in this set are really, there's a lot of stuff that pops up throughout the course in the HSC exams and assessments and things like that. And they're called the Pythagorean identities, which would make you think about a squared plus b squared equals c squared, right? Like the right angle triangle Pythagorean theorem, which is what it is. Now, if we look at this triangle here, we've got a right angle triangle tracing around here. We've got x, y, and 1, which gives us x squared plus y squared is equal to 1. But then the other thing we know is that sine theta is equal to y and cos theta is equal to x. This gives us this absolutely kind of fundamental relationship of sine squared theta plus cos squared theta equals 1. Now, it doesn't have to be theta. It could be any variable, x, y, z, t, whatever. This is a fundamentally important. Now, a couple of points I'll say. When I have sine squared theta, what I mean by that, what I'm squaring is not the sine. It doesn't make sense to sine. This is the convention of saying, to avoid having to use brackets, sine theta all squared. Because if I wrote it like this, is it theta squared or, sine of x squared? Like, these are confusing, right? I don't understand what might be happening. Question mark, question mark. So we write it like this. We put the sine next to it, so that means this. Sine of theta all squared. If I wrote sine x squared, I would be saying it's sine of x squared, right? So make sure that you write sine squared theta plus cos squared theta equals 1. That's a fundamental Pythagorean or trigonometric identity, which I've written here in terms of x, right? So again, it doesn't really matter what the variable is. It all means the same thing. It's always true, right? So no matter what the angle x, if I do sine squared plus cos squared, it will always give me 1. Right, now this leads us actually to a couple of others. If I go over here and I say, okay, sine squared x plus cos squared x equals 1. Now let's say divide everything by cos squared. I divide everything by cos squared. I'll divide this by cos squared x. If I do that, then I'm going to get the following. Sine squared x over cos squared x plus, now cos squared divided by cos squared is 1, equals 1 over cos squared x. Sine over cos is tan. Tan squared x plus 1 is equal to 1 over cos is sec. Sec squared x. So here is another identity that we can use and then of course rearrange in all kinds of ways. I mean, this one could be, I'll just write quickly over here. This could be tan squared x is equal to sec squared x minus 1, or any number of other ways that you could do it. 1, tan squared minus sec squared is equal to 1. No, it's sec squared x minus tan squared x equals 1. All right, so it's just rearranging. But this one is a division of cos squared. Now, if I then take this and I say, well, what if I divide both sides by sine squared? Sine squared x plus cos squared x equals 1. If I divide both sides by sine squared x, what would happen? Well, we get a different set of ratios and their identities. Sine squared divided by sine squared is 1, plus cos squared x over sine squared x equals 1 over sine squared x. And if I do that, this becomes 1 plus cos over sine is cot equals 1 on sine is cosec. I suppose cosec squared in this case. And so we have another version using a relationship, an identity between cot and cosec. So sine squared plus cos squared equals 1 is linked to tan squared plus 1 equals sec squared is linked to 1 plus cot squared equals cosec squared. And so these three are related and we use in different types. So let's have a go at a couple of examples. I'm going to simplify the following. Sine squared alpha cosec squared alpha. Well, this one's not actually using the identity. It's just a bit of a trick. I mean, we could do that, but basically it becomes sine squared alpha times, well, cosec is 1 on sine. So this becomes 1 over sine squared alpha. Well, it's multiplied by its reciprocal, so the answer just becomes 1. All right? I'll just put here cosec alpha is equal to 1 on sine alpha, which means that if you square it, then it's also going to become the square is equal to 1 over the square of the other. So that's a simple one that we have. Now let's have a look at this one. 5 cot squared theta plus 5. What's that equal to? Okay, well, the first step is we've got this 5, so let's factorize that out. And I'm going to get cot squared theta plus 1. Now, if I go back up to my set of things that I had, I've got sine squared, cos squared, tan squared plus 1, sec squared. 1 plus cot squared, or cot squared plus 1 is equal to cosec squared. So this is actually equal to 5 cosec squared theta. It simplifies. And why is that good? Because instead of having two things, you only have one thing. So it's better, right? It's easier. So this thing here is equal to cosec squared theta. And so we end up with that simplified answer. Now the final one, the formatting of the book seems to be a bit messed up. These all should be thetas. Don't be overly worried about that. If you see it, just assume it is the same variable. So it's a prove that question. Prove that means that we have to start with the left-hand side, start with this, and do stuff to it that ends us up back on the right-hand side. All right, so we can't go between the two. We have to start with the left and end up with what's on the right. So that's what we're going to do. So cot theta plus 2 sec theta is equal to, now as I said before, you notice that all this stuff is sine, cos, right? So I'm going to put that in, and it's one single fraction. So I'm going to go ahead and do that. Cot is cos theta over sine theta, whereas tan is sine theta over cos theta. Cot is cos over sine, plus 2 sec theta is 2 times 1 over cos theta. All right, 1 over cos theta. So we end up with that. Okay, because sec is equal to 1 on cos. Now notice this is going to become cos theta over sine theta plus 2 over cos theta. I want to bring them together. So I need to multiply this one top and bottom by sine theta to match the denominator. Excuse me. And this one I have to multiply by cos theta on top and bottom to match the denominators. So here's what's going to happen. We're going to get cos times cos is cos squared theta over sine theta cos theta plus 2 sine theta over sine theta cos theta. Now we've got the same denominators, which you notice is what's up here. So we're getting to the point where we need to get. So I'm going to get cos squared theta plus 2 sine theta over sine theta cos theta. Almost there. The final part is to use this thing. And from our identities before, I'll just put over here, sine squared theta plus cos squared theta is equal to 1. So cos squared theta is equal to 1 minus sine squared theta if I rearrange that. So the final step is that the cos squared theta is going to become 1 minus sine squared theta plus 2 sine theta over sine theta cos theta. And there we have it. We've shown as required. We've proven that those two things are equal because I started with what was on the left and I ended up with what was on the right, exactly as is. All right, so see if you can follow through with that. A lot of it is to do with using identities, making it into things related to sine and cos. It is a bit tricky, but this is worth working on because it comes up all the time. Thanks, guys.